So I'm presenting our work, Aerial View Localization with Reinforcement Learning, towards emulating search and rescue. This work was done together with Anton Samuelsson, Jon Baxen, and Kalle Åström at Lund University. The motivation behind our work is the broadly increasing use of UAVs within a bunch of environmental monitoring applications and other regimes, such as search and rescue. So with intensifying climate breakdown, we will see and are already seeing an increased frequency and severity of natural disasters. A safer and more effective approach than humans operating on the ground, UAVs could be used to do certain parts, at least, of the search and rescue operations instead. The question is, how should the UAVs localize, for example, a group of missing people, especially considering that GNSS systems may be unreliable or unavailable, in particular, for example, in conflict-driven areas. So the question, or sort of the higher level question that we have when considering this work is, assuming we have a set of missing people who have been able to give some form of description of their whereabouts, such as some form of visual cues, how should a UAV explore a given area to efficiently find these people? In the longer term, we imagine, for example, a possibility where you have street-level imagery of a disaster-hit area, which is given to the UAV, and the UAV that hovers above and has a downwards-facing camera would then use that visual information to precisely localize this position in an area. But we begin in a somewhat simpler setup, which I will first explain by this example here and then provide some more details into. So assume you have this given search area indicated as a black rectangle, and that you have a UAV that is positioned in some certain starting area, which we call step 0 here. Now we're given some visual cues about our goal location, and in this work we consider the visual cues to be given as a top view patch from the search area as a simpler starting point. And assuming we have a discrete setup, which we do in this work, we can start considering kind of like a sequential decision-making task, where you have an agent that is resembling this UAV that moves around in this area and explores it step by step until hopefully reaching the goal location, such as in this example, which is successful, and the agent is able to localize the goal very efficiently in a few movements. And note again that we should keep in mind that in many real-world applications with UAVs, you have many restrictions, such as time and battery constraints. So you want to solve this task as quickly as possible and not resort to exhaustively looking everywhere in the search area. So in this work, we introduced the task of aerial view goal localization, which is a first step towards emulating UAV-based search and rescue. And it can also be used more broadly within other applications. We provide an idealized setup that allows for controllable and reproducible experimentation, which is very useful in this earlier stage of development. Specifically then, we're considering a discrete setup where you take this search area and you discretize it into an m times n grid of non-overlapping grid cells that you can move between. You assume that you have an agent that sequentially moves around the area, and it only sees partial glimpses of the area as it moves along. The objective then, or the task, is to localize a patch within a limited movement budget, T, which is significantly smaller than the overall search area, so that we avoid trivial solutions like exhaustive search. I now present our main approach that we consider in this paper. We consider a reinforcement learning-based model that we call airlock. Airlock operates in a given environment, such as the one shown on the left. Assuming it stands in the position called current, indicated now with the red rectangle, it only sees that part of the area right now. And in that area, it sees the observation, OT, the top view patch, and it also is given positional information. But the positional information is sort of egocentric and relative to the overall search area. So it's not given global positional information or anything like that. The goal is also observed at every stage. So you have the visual cues for the goal, but you don't know where it is. We begin in the policy network of the agent by computing some semantic information using a segmentation network. And the output from that network, including the raw observations themselves, are fed to a patch embedder, which I will explain on the next slide. The patch embedder outputs context features, CT, and a so-called exploitation prior UT that I will come back to. We take the context information CT and we take the positional information PT and feed those to the temporal unit together with UT. And this is then propagated forward to the decision unit, which issues an action AT, which takes you to a next movement or next position within the overall environment. And during training, you're also provided a reward, which incentivizes moving to the goal as quickly as possible, essentially. I forgot to say that the temporal unit is in this work an LSTM, which integrates information over time as the search proceeds. So this patch embedder, we realized quite early in experimentation that we would need some pre-training phase for the reinforcement learning system. And this is quite common in many visual representation learning setups. And we found this earlier work by Dorsch et al., who consider a self-supervised task for visual image classification and similar. It can be explained quite easily by this cat example, where you assume that you have a neural network which observes the blue patch, the center of the face, and then it is provided another nearby part of the cat, for example, the ear that you see there. And then the neural network should figure out the relative positioning between these two patches. And in this case, the correct is position number 3, so to say. And we noted that this is very similar to a special case of our setup. And the special case that is if you have the start and goal adjacent to each other, then it becomes very similar to the previous self-supervised task that I introduced. So therefore, we decided to try that approach. We generated a bunch of self-supervised mini games, if you will, that were trained without reinforcement learning, but just as a self-supervised learning task with like an 8-dimensional softmax in the end for the 8 adjacent possibilities. And it indeed improved results quite a bit. Now, I mentioned that this patch embedder outputs both the context features and this 8-dimensional, guessing which is the adjacent position. So we have the context features CT in the system that I talked about, and then we have UT, which is the 8-dimensional action proposed by the patch embedder, and we call that the exploitation prior. And I will come back a little bit later in the results to show the effect of this. But it is helping the agent to provide it actually as a shortcut connection to some of the other sub components of the policy like that. Moving on to the experimental results. We have the following baselines. First of all, we have a random model, which just takes random actions until reaching the goal or exhausting the budget. But we call it privileged random because we also make sure that it doesn't move to previous locations and not outside the image. Different to our airlock system, which is able to move to previous locations and outside the image, even though it often learns to not do so throughout training. We also have privileged local, which essentially take the patch embedder that I talked about, and during inference, you just feed the current patch and the goal patch repeatedly, step by step, in every new position, to this patch embedder to give a new suggested action and a new suggested action all the time until either you succeed or fail. So essentially, you can imagine that when the current is getting closer and closer to the goal, then it essentially gets better at its task because it was trained in that particular setting where they are adjacent. We also had roughly 20 humans who participated in playing this game, so to say, so we can also compare those with the other methods. We did evaluations on 3 different data sets, and the C sensitivity for the reinforcement learning systems is low overall. The first set of results on a 5x5 setup with 10 movements as budget, corresponding, by the way, to roughly 500 by 500 meters in the real world. On the y-axis, you have the success rate, higher is better, and on the x-axis, you have the initial distance to the goal, which can be between 1 and 4, given that you have a 5x5 setting. First of all, the success rate generally decreases as the distance to the goal increases, as can be expected, because it gets more difficult. The main airlock model outperforms some of its ablated versions, and I will briefly mention some of these ablations now, but there are more in the paper. So specifically, we were considering removing certain parts of this exploitation prior that I recently talked about. So the first version is that we call no residual. It omits the using it in the decision unit. And why it's called no residual is because if it is used, we call it like a residual connection. And this is because the decision unit essentially has to learn only kind of the residual between the output suggested by the patch embedder and the reinforcement learning system. And then we also omit it altogether in another ablation, and we call that no prior. So that's what we see. Airlock outperforms its ablated versions. And airlock also outperforms this privileged local approach on average and in most start to goal distances. The exception can be seen at precisely when the goal and start are adjacent. There you can see that priv local is slightly better. But that is also the regime where it was trained, this priv local method. Humans turn out to perform quite poorly on the task, especially compared to the aforementioned methods. And this indicates that this task, even as the 5x5 scenario, is difficult, and it motivates further research into this direction. Similar results carry on to the 7x7 setup, where we took the airlock model that was trained in 5x5 to see how it generalizes to 7x7. And airlock is still the best approach among the alternatives, so to say, even though priv local does outperform it at the sort of smaller distances to the goal. Moving on to some visualizations on a disaster dataset called the XPD disaster. So here we have top view imagery of different areas after different types of disasters. This is a flooding scenario where the airlock model is located here. It's given this type of goal observation, takes a first movement, probably fairly randomly, and then it sees quite a bit of this green forest area, and it decides to move further into that direction, and eventually finds the goal location in 4 steps. And this was the underlying scenario, so to say. Priv local, on the other hand, is also successful, but it's doing it a bit more slowly, so in 5 steps instead of 4. Now we look at some further visualizations, and in this case we can see the red airlock and green priv local method move at the same time, so we can compare. So first step is the same, then they diverge, and airlock reaches in 3 steps, and priv local has to take 6 steps before it succeeds. Taking a larger 7x7 area in a wildfire scenario, doing the same analysis, you can see how it goes. So airlock did it quite much faster than priv local here. And this is another post-flooding 7x7. Airlock again more successful. And then, of course, we have a bunch of scenarios where the methods fail, given the difficulty of the task. So in this work, we introduced and tackled the task of aerial view goal localization, which allows for controllable and reproducible experimentation. We proposed a fully trainable reinforcement learning-based approach called airlock. And this system generalizes to scenarios of depicting disasters, even in the cases where it was trained on non-disaster scenarios only. We presented the work at the Machine Learning for Remote Sensing workshop at ICLR 2023. And the work was also accepted for SICE 2023. Code models and pre-processed data have been made publicly available. Thank you very much for your attention.